Thanks very much, Keith. Yeah, it's great to be back here amongst all these friendly, familiar faces. So, yeah. So actually, this is the very first slide sort of shows a little bit, this is the familiar drunk under the lamppost story. So I admit to actually sort of doing some serious lamppost looking under here, right? This is, non-parametric Bayes was the flavor of the month, maybe a year or so ago. And so this is me as someone that likes to think about grammars, trying to think about how one can we do anything interesting with these non-parametric Bayesian methods? So I admit to that, to being a lamppost looker under. So what are some of the ideas here, right? So I think actually the non-parametric Bayes stuff really is interesting because, standard parametric learning methods, and I'd say at least all the successful methods I know about really are sort of reducing learning to optimization. So you wind up having a vector of parameters. You've got some objective function. And essentially what you have to do learning is to find the values of the variables in this vector of variables that optimize some objective function. And that's really what learning boils down to. So for example, in general, the way in which people wind up modeling learning of PCFGs is you imagine you start off with some superset of grammar rules, and then you're going to try and use a parametric estimator to try and estimate the probabilities on those rules, and then you'll keep the rules that have probabilities that pass over some threshold. So non-parametric estimation techniques have the potential, I think, to sort of provide us with a systematic way of actually learning the parameters as well as learning the values. So that's what non-parametric means here. Just out of interest, how many people have seen things like Chinese restaurant processes and stuff like that? So we're pretty much so I can assume that it's moderately familiar here, right? So as you guys then would know, when you're actually sort of doing these type of estimation, MCMC methods are relatively natural. The second half of the talk, which I can spend more time focusing on, is actually on some of the methods which we've actually had to sort of develop in order to, inference is the big problem, and some of the methods that we've developed to make inference more efficient. Okay, so in the version of the talk that I wind up giving to linguists, actually, I put this up actually saying that I'll sometimes even say more strongly that Chomsky should be a Bayesian, right? Because Bayesian inference is actually, I think, sort of fairly natural. The posterior decomposes into these two terms, into a likelihood term, which is data-driven, and then the prior, which encodes the information that you've got about the learning problem before the learning task actually even starts. But of course, what makes this tricky is that in general, you're wondering when you're doing this inference, you're in a situation where there's infinitely many possible grammars. Okay, so how many people haven't seen context-free grammars before? Everyone's sort of seen them. So basically, they have rules that look like this over here. They generate trees that look like this. The probability of a tree is the product of the probabilities of the rules that are used to build them. Is that relatively clear? And so we can use them to describe fairly simple models of what's known as phrase structure. Good, so let's go on. So it turns out that there are lots of sort of fairly standard Bayesian techniques for doing PCFG inference. They work really well on artificial data. They work really badly on real language data. There's lots of reasons why, you can come up as post hoc rationalizations as to why they might do badly. The strategy I've been taking for a while is to say, gee, maybe in fact actually we could learn something by studying simpler cases. And in fact, I'm going to start off worrying about just the morphological segmentation case. So basically I'm going to say, all right, I want to try and see if I can learn, given a bunch of inflected forms like walking, I want to try and see, or walks and walked, those things. I want to see if I can learn that the walk is a stem and ing is a suffix. And if I can do that, I'll declare success. right? I'll get a little bit beyond that in this talk, but let's start off there. And it'll actually sort of show us what some of the problems are with context-free learning models. So if your goal is actually just to reflect, to build a tree that can encode the correct segmentation here of talking into talk plus ing, this tree here will in fact actually do it. So this tree, this grammar is going to be the sort of grammar we'll work with for a while, right? So the grammar says that a word consists of a stem followed by a suffix, and stems and suffixes are both generated by sequences of characters, and characters are generated by this right branching tree structure over here. That's just a sigma star, essentially. So, yeah, I mean, what you can see over here is these trees certainly can represent that segmentation. But I would hope all the computational linguists in here would sort of be boggling at this stage, right? Because in fact, actually, these trees over here, even though they can represent the distinctions we're interested in, there's no way that these PCFGs can actually learn that. And the reason why is because inside of a PCFG, the parameters are associated with rules, but the rules here are too small a unit of generalization, right? So this PCFG can learn things like the probability that n is a character, but that's not what I want to learn. I want to learn the probability that talk is a stem, but there's no single rule that encodes that here. So no matter how I tweak these parameters, I can't learn the generalizations that I want to learn. So what you really want is something that looks like this, that says that a word consists of a stem and a suffix, stem expands to all possible stems, suffix expands to all possible suffixes, and at this stage, you guys should be keeping your hand on your wallet. In fact, I gave a presentation at the University of Arizona where I used this example, and somebody in the audience said, yeah, I should put your hand on your sidearm, right? Because there's an infinite number of possible stems and possible suffixes, right? And so this is no longer a context-free grammar, because you need to have a finite number of productions. But there's actually a sense in which, so first of all, it should be clear, right, that here we can, with these sorts of things, we can in fact actually learn the probability that stem rewrites as TALK, which is exactly the sort of thing that we do want to learn. But there's a sense in which this is not even though this is no longer, this is not a, because there's an infinite number of potential rules, it's not a real problem here. And the reason why it's not a real problem is because actually, given any particular data set, there's only a finite number of stems and a finite number of suffixes that you could possibly find in that data set. And in fact, actually, this sort of says that, gee, if I actually get to pick the rules after I've seen the data, if I let the data choose the rules that I want, then in fact, actually, there's not really any problem here at all, right? And there's a sense in which actually that's sort of one of the intuitions behind this non-parametric work. We're going to let the data pick the rules, as well as picking the rule probabilities, right? Okay, I want to now show there's still a few more problems here. So, okay, all right, if I said that stems consist of all possible sequences of characters, suffixes consist of all possible sequences of characters, we do this thing that I just said before, well, I'll only look at the subset that could possibly be used to generate the data. Now can I throw my PCFG learning procedures at it? Will it work? Will it find the right segmentations? In fact, it turns out it won't. It's fairly easy to show that if your goal is just to maximize likelihood, the ML solution is always going to be the so-called saturated models, which wind up saying, say, for example, that every word consists of a stem and the suffix is always null. These saturated models have one parameter for each possible word type down here. So in fact, they can actually nail the empirical distribution exactly. And there's a theorem that says essentially that maximum likelihood tries to minimize the KL divergence between the predicted and the empirical distributions. And if you can fit the empirical distribution exactly, then you get zero KL divergence. And in fact, actually, you can show that EM methods, for example, which try to maximize likelihood, they do in fact actually find this trivial solution. So we're still not there. Okay. So, I started off talking about how Bayesian inference is great. So all of you are probably thinking, well, we know how to use Bayesian priors to enforce sparse solutions. And so the way in which you can do that then is you can say, gee, I'm going to have so here you can see I started off, if I put a Dirichlet prior, the uniform Dirichlet prior looks something like this. As these alpha values start to get smaller in the Dirichlet, what actually happens is that the prior becomes increasingly concentrated around 0. What that says, essentially, if I use a Dirichlet prior on a rule that looks like this, what this says is, actually, I really prefer grammars where this rule has probability 0. In other words, where I've learnt to turn off the rule. So you can think about these Dirichlet priors as letting us do a type of feature selection. And in fact, those of you that do Maxent with different types of, L1 regularization, they're essentially using a prior to do feature selection for you too. I think you could use an exponential prior. It would make inference harder because the Dirichlet is conjugate to the multinomial. So that lets you actually integrate out the rule probability parameter. But at this sort of conceptual level, you could certainly do that. I've actually played a little bit with a few other priors to see if they have properties that might be useful. No, in fact, actually, so it turns out if they're conjugate, it really gets, what actually happens is the inference really just boils down to, taking the same expected counts that you get with something like EM, plus adding these Dirichlet counts. These become like pseudo counts. And if you want to do variational Bayes, then you pass it through a squashing function. So there's no linguistic justification for saying the Dirichlet is more plausible than anything else. Let's see, let me think. Noah Smith actually, I think, has done some experiments on some non-conjugate priors, and on some applications he's been talking about, he actually claims that he gets, for learning dependency grammars, unsupervised induction of dependency grammars, he actually claims that an entropic prior, in other words, so given these rule probabilities theta, you can define the entropy, for each multinomial, and then I think he winds up saying, gee, I want an entropy which is as low as possible, which means that it's going to be as concentrated as possible. And he claims that for his dependency grammar induction, I mean, I've got no reason to disbelieve him, I'm just saying, he says for his application that the entropic prior does better than the Dirichlet. The math becomes more complicated because it turns out you can no longer just analytically integrate out these things. So, yeah, here I'm doing some serious lamppost looking under, right? Okay, all right, so here we go, a little experiment. I'm going to sort of crank this alpha down towards 0. Let's check to see what they look like. So this is where basically I've taken all the verbs from the Wall Street Journal. And so you can sort of see over here with alpha's fairly large, there's no segmentation whatsoever, so I'm still getting the maximum likelihood segmentation. As alpha starts to get smaller, I'm starting to pull off some suffixes, but it's still not great, right? I mean, including is still sitting here. And some statisticians pointed out to me that if I'm using an alpha of 10 to the minus 15, I should do 10 to the 15 iterations at least before I should expect convergence. So you should not believe these numbers over here. But in fact, the point is that even the Bayesian sparse prior is really not coming up with anything reasonable here. So why isn't it? Well, one way you can sort of take a look at it is, here's the Dirichlet prior parameter. I'm looking here essentially at the posterior probability as a function of alpha. And what I can actually do is I can plot it for null suffixes down here. So this is no segmentation. The true suffixes, because I know what the goal segmentation ought to be. And then these are the optimal suffixes that my search procedure finds, right? And so you can see essentially that the true suffixes are like many orders of magnitude of probability separated from the ones that the search procedure is finding. So the search procedure is not guaranteed to find the optimal ones, of course, still a heuristic search, but the fact that, so the optimal one is still further up there. So what this is actually showing is that in fact the model is just plain wrong, right? I mean, so that's that point there. So what's wrong with it? Well, it's such a simple data set that we can in fact actually try and figure that out. And one of the things that's wrong with it is that the model basically assumes that the probability of each suffix should be the same independently of the stem. So here I've just simply plotted the probabilities of different suffixes for a few fairly high frequency stems. If you actually calculate the error bars in here, the error bars are not really visible. Their frequencies are so high. So in fact, these differences here are incredibly significantly different, right? So in other words, what this is just simply saying is that, a verb like expect appears more frequently, or including appears far more frequently than, what's this one over here, expecting. And that's sort of pretty obviously true. So the model has built into it independence assumptions that just simply aren't satisfied in the data. You see far more diversity in frequency than the independence assumptions in the PCFG model would predict. And there's a number of ways of trying to deal with this. One method that we've been looking at is to say, gee, maybe in fact what you really ought to be doing is inference from types rather than tokens. That is, you want to sort of try and dampen the frequency variation. So by types, what I mean is if the data is something like, the cat chased the other cat, you can see the types and the tokens listed here. So if you do inference from verb types, then because if there's only 4 common verb suffixes, then in general each suffix is going to appear with a frequency of about 0.25 in types. And in fact, these types of reasons actually have led some psycholinguists to actually propose that people learn from types rather than tokens. And in fact, actually, if we do exactly the same procedure, but we run it off verb types, then in fact, actually, we discover that the segmentations come out looking actually sort of quite good. And in fact, even some of the things that count as errors in the actual procedure actually are sort of fairly plausible. So, the reason why this E is pulled off here in continue is so it can capture the ing generalization in continuing, right? So it generally looks sort of pretty good. And then if you look at the same posterior probability plot over here, you actually sort of discover that in fact the true suffixes, sort of wind up lining up with the optimal suffixes. So again, that's exactly what you'd sort of hope for, yeah. Where are we? Oh, down here. So I think what happens is that as this starts to as this alpha gets low, it's starting to become far more. I think in fact it's starting to pull off a prefix here. I don't know what's happening down there. Yeah, but in fact I think if you actually look at the plot on the next, on the next one over here. You can actually sort of ask what value of alpha turns out to be sort of close to optimal, and in fact, I didn't plot it at 10 to the, I didn't give you the solutions at 10 to the minus 3, but this is 10 to the minus 5 over here, so in fact, somewhere in between these two is probably where the model's giving the best results. So anyway, so basically, here what we've identified is sort of 2 problems with the standard, independence assumptions inside of PCFGs and HMMs, right? So one is that the rules often tend to be too small to be effective units of generalization. So you really want to generalize over groups or entire subtrees. And then the second problem is that that in fact actually sometimes you want to be able to dampen frequency variation. You want to be able to do type-based inference rather than sort of token-based inference. No, it doesn't. It doesn't come for free in this case here, right? So one thing what you could try to do is to essentially, you can build a mixture model inside of a PCFG. And so you could then try and have, say, for example, suffixes that tended to have low probability, suffixes that tended to have medium probability, suffixes that tended to have high probability. So you could try and do that. In fact, before we started doing this, we in fact tried that sort of mixture model. But it certainly does better than the model without that. I mean, the mixture model can fit a greater diversity of probabilities. I'm a little, I actually think that there are two ways of making models like PCFG non-parametric, and in fact they're not exclusive. They can in fact actually be combined together. The mixture model approach corresponds to something that's like state splitting, where you don't know how many mixture components you need to put in. And that's where things like LDA and those types of methods go. I chose not to focus on that within these adapter grammars, but in fact I think that's obviously a very successful and very, I'm not going to say that stuff is bad, right? I think that's also it's been a very productive line to go. Yeah, all right. So now I'd just like to sort of briefly remind you guys about Chinese restaurant processes, that they're the extension of, if you take a Dirichlet multinomial and extend it to an unbounded number of outcomes. Would it make sense just to briefly go back over Chinese restaurant processes? Okay, all right. So again, just imagine that we just actually had a finite number of outcomes. So this is like, just imagine that, Mussie's rolling a die, but it's this rather strange old Italian die, so I don't know how even it is, right? So I want to estimate the probability on the different sides of it, right? So that's what these Z's are over here. So I've seen rolls Z1 through Zn, and I want to predict the probability that Zn plus 1 is K. And if I have a Dirichlet prior with parameter alpha sub K, that's, in other words, it's the pseudo count for side K, and I've seen side K n sub K times in my observation sequence, then the predicted probability for seeing a K on the nth plus 1 roll is going to be proportional to alpha K plus nk, right? Pretty straightforward. Okay, so the logic behind the Chinese restaurant process says, okay, what happens if I let the number of sides on this die go to infinity? So I now want to imagine that there's a very strange die that Mussie's presenting me with. I can't even count the number of sides on it. So this is kind of like if I'm trying to do clustering, I don't know how many cluster components I might need, for example. So as I let the number of sides go to infinity, and I'm keeping my data set fixed, what's going to actually happen is that most of the outcomes are not going to be seen in my data set, right? As, if n is equal to 100 and m is equal to 1,000,000, I'm not going to have seen 999,000, whatever it is, outcomes. So I can actually then ask, okay, so what's the probability of seeing an outcome that I have seen before? Well, this alpha over m winds up sort of going towards 0. So it's going to be, essentially this alpha sub k term winds up going to 0. So basically all the probability of seeing some previous outcome is just going to be proportional to the number of times I've seen it before. The probability of seeing some other outcome that I haven't seen before is going to be proportional to alpha divided by m. Right, so that's because my pseudo counts now get divided over these m different outcomes over here. So two things to remember. So first of all, the probability of seeing a previously seen outcome is proportional to the number of times you saw it. The probability of seeing any outcome not seen before is m times alpha divided by m. So it's going to be proportional to alpha. Right, so now my Dirichlet parameter essentially is telling me how likely it is that I'm going to see some unseen outcome. So the idea behind Chinese restaurant processes is that if I'm doing something like clustering, the actual sides of the die are really kind of meaningless. I am the person that, it's the data that's in the cluster that gives meaning to what the cluster is. The clusters are otherwise equivalent. So I can imagine, say for example, Mussey's rolling this funky Italian die. I can't even count the number of sides on it. Every time a side comes up, I write the label on it. So Mussey's die starts off initially completely unlabeled. He rolls it the first time, and I go, okay, all right, I'm going to call this side number 1. So I'll label that 1. Mussey rolls it again, and then according to this formula over here, I'm going to say the probability of seeing side 1 again is going to be proportional to the number of times I saw it before, namely once. The probability of seeing some fresh outcome is going to be proportional to alpha. When Mussey rolls it again, if it's a fresh side, I write a 2 on it. And now I know, now I've identified 2 sides on this die, but I'm the one that's identifying those sides. So this basically is now, we've now gone from multinomials to Chinese restaurant processes, where the probability of seeing some previously seen event is proportional to the number of times you saw it. The probability of seeing a fresh event is proportional to alpha. And then the Chinese restaurant processes are normally sort of shown with this type of analogy over here, right, where you wind up saying, essentially I'm sort of learning this customer to table mapping over here. So we're starting off with an empty restaurant, and then the first customer, the rule essentially is that a customer sits down either at an occupied table with probability proportional to the number of people sitting at it, that's this part of the formula over here, or sits down at the first unoccupied table with probability proportional to alpha. So since there's nobody in the restaurant, they have to sit down at the first unoccupied table, like that. And the probability of that is alpha over alpha. So second customer comes in, they can sit down either and when the second customer is coming in, with probability proportional to 1, they sit at the first table. With probability proportional to alpha, they sit at the second table. So the probability of this particular arrangement is going to be the previous probability times 1 over 1 plus alpha. Is that relatively sort of straightforward? So we keep on going like that. So now, and you can now imagine, in fact, this is like the set of rolls of die from Mussey's die here that we're seeing here. So we've now rolled a 1, 1, 2 because the third customer sat at this table 2 up here. And so on like that. We actually have got some interesting performance improvement by using Pittman-Yaw processes instead of just Chinese restaurant processes. So Pittman-Yaw processes are slightly more complicated. Chinese restaurant processes, the thing that I just described for you, have a very strong rich-get-richer effect. What tends to happen is that just a few tables will get all the customers. And Pittman-Yaw processes can be regarded as sort of having a Robin Hood system where basically each table, you decrement its count by some number A over here, and you're going to give the mass from that table to the next unoccupied table. So that's going to make the system become more encouraged to posit new tables over here. And so you can see if there are M occupied tables, I'm taking mass A away from each table, then I wind up giving mass MA to the next unoccupied table. And so the formula then winds up looking something like this. So this B, here I'm just simply copying Pittman and Yaw, who call their parameters A and B. This B is in fact exactly the same as that Dirichlet alpha that we saw before. So, you have to sit at that first table. Now, in fact, you can see the probability of sitting here is not just proportional to 1, it's proportional to 1 minus alpha, 1 minus A. And so on like that. So this sort of sees the formula out here. Okay, so far what's actually happened is that, I've been just treating the labels essentially as arbitrary integers. These processes get really interesting when you actually use them to generate not just sequences of integers, but you actually use them to generate sequences of arbitrary other things. And the most straightforward way of doing that is to imagine that the tables get labeled with something. You can imagine, if you want to carry out the restaurant analogy, you imagine that in fact actually each table has a dish of food that's placed on it. But there's some other process that's known as the base distribution, this P0, that's responsible for essentially generating labels up there. So, so in terms of the table to label mapping over here, what you'll actually see is the same sequence of integers that we've got before. So this is now we're imagining that instead of me writing numbers in order on the die, on the sides of the die as Massey rolls them, what in fact I'm actually going to do is I'm going to stick, I've got some set of objects, an urn or something which contains little stickers. Every time Massey rolls his die and turns up a fresh side, I get a sticker that I just draw out of that pot, and I stick it on that side. So we start off, first customer comes in, and I might decide to put some fish on that table up there. I generate the word fish. So now the probability of, I'm generating the output sequence fish is the sequence of tables I've seen over here as 1 as before. Now the probability of the output sequence is the probability of assigning the customers to these tables times the probability of generating this particular labels on the table. So it's whatever the probability is of generating fish from my base distribution. Okay, now when the second customer comes and sits down at this table up here, there's already a label on this table over here, so I don't need to regenerate that same label again. So you'll notice even though I've generated the word fish twice over here, I've only paid the probability cost once for generating that label. On the other hand, now when the next customer comes in and sits down at this table over here, I need to generate a fresh label for it. I could in principle generate even the same word fish again. It depends on what P0 is. There's nothing that says these labels need to be distinct. But I wind up paying the probability cost twice. I wind up paying the cost for 2 labels. All right? Yeah, they're independent draws of P0 at this stage. In fact, what's actually going to happen, of course, is that I'm going to be generating these tables and their labels conditioned on some input sequence. And then all of a sudden that couples all of that stuff. But at this, I'm giving you the generative model here now. And so under this generative model, they're independent. Yes, in fact, actually, another possibility is to imagine that the tables come pre-labeled. Yeah, exactly. Okay, and so that's how the sequence goes. So just to sort of summarize, so basically CRPs generalize us to an unbounded number of outcomes. They've been heavily used before in terms of clustering models where you sort of use the CRPs to generate the right number of clusters that you wind up using. Pitman-Yaw processes generalize CRPs by having this discount parameter, essentially that lets us describe a wider set of distributions. By using this labeling mechanism, we can actually use CRPs and Pitman-Yaw processes to essentially sort of generate distributions, not just over integers, but over essentially arbitrary sets of objects. Okay, I think I'll skip that here. That's about the relationship with Dirichlet processes. So there's 2 sort of obvious ways, if you imagine you're starting off with a grammar, of making it go non-parametric. One way, I don't know how many people here have come across the infinite HMM. So the infinite HMM uses essentially state splitting. So the idea is that you start off with some base hidden Markov model, which has some number of states in it. But the actual states that you wind up in the machine you wind up learning essentially are refinements or splits of the states in the original machine. So what you could imagine essentially is that in terms of a PCFG, is you say, okay, I start off with a PCFG that's got rules like sentence goes to noun phrase, verb phrase. But in fact, actually, that's not the grammar I'm trying to learn. The grammar I'm trying to learn, in fact, actually has split the sentence category into maybe 100 different sentence categories. And so I'd learn, say, something like sentence sub, with split 35 goes to noun phrase under split 27 and verb phrase under split 17. So, And in fact, actually, this is what's been called the infinite PCFG. Another way of making PCFGs non-parametric is to imagine that so this is essentially saying that the number of non-terminals can grow unboundedly. Another way of doing it is to say, let's let the number of rules grow unboundedly. So we'll say, in fact, actually, that new rules are compositions of several rules from the original grammar. And that winds up saying, essentially, that we're going to cache entire tree fragments. We're going to wind up learning probabilities, not just of rules, but entire tree fragments. And that's actually what I'll call adaptor grammars down here. And the two ideas are quite compatible. You could, in principle, do both, although, as far as I know, nobody has. So, oops. So the informal sort of description is that we wind up saying that inside of an adaptor grammar, the trees that are generated by an adaptor grammar are the same as the ones that the base CFG generates. But you, as the designer of an adaptor grammar, need to identify some subset of non-terminals as adapted. The unadapted non-terminals expand just as in an ordinary PCFG. That is, you pick a rule proportional to its probability and rewrite the non-terminal. But the adapted non-terminal can expand in two different ways, either just as in a PCFG, or else it can just simply reuse an entirely, a subtree that you've used before. So the adaptor grammar, in a sense, sort of caches entire trees. And that's implemented by having a CRP or a PYP for the adapted non-terminal. So let's actually see how that might work for this little morphological segmentation example over here. So we want to learn how to, we want to generate words in terms of stems and suffixes. So the first customer comes in, we need to generate the first word. You can imagine that these rules are kind of like recipes. So this says that in order to put a word label on that table over there, we need to find a stem and a suffix. This is a funny sort of restaurant because these guys order out. So in order to generate a stem and a suffix, we send out customers to the stem and the suffix restaurants. They say, give me a stem, give me a suffix. We've got the recipes over there that say stems are sequences of phonemes and suffixes are sequence of phonemes. So we might generate cat and s, bring them back, and then we have the word cats on that first table up there. The second customer can come in. Now we need to repeat the entire process to generate a label on the second table. And again, we can order out. Now we can say, okay, I'm going to reuse the suffix that I used before, but I need a fresh stem. So I might generate dog, and now we generate dogs. The third customer comes in, and then it can sit at the same table. So now we've generated cats twice. But you'll notice that, in fact, we didn't go through this, we just reused the entire subtree. We didn't go through the stem and the suffix again. So what this actually means is that when we're learning stems and suffixes, we're learning them from types rather than from tokens, which, as I said before, is sort of one of the goals that you want in something like this. So an adapted grammar basically sort of says that it's interesting that the sequence of trees that are generated aren't actually independent of each other. And that's because if it's generated a subtree before, you're actually far more likely to reuse it. And that's because it's actually learning from the trees that it's generated before. So over here you can see the rules that are used for that sort of expansion here. This winds up actually producing a model which actually naturally generates Zipfian distributions, which I think is sort of kind of interesting. If a Martian linguist came and looked at human languages, I think one of the first properties they would note is the Zipfian distribution that we've got. But as far as I know, this is like the first, generative model of human language that actually generates Zipfian distributions. I think I'll skip this here. Let me just sort of show one other, actually, maybe, let me go back here. Let me just skip over this word segmentation and just simply show you one other application that we've been playing with for a while, which is trying to learn structures of named entities. So in this little grammar here, we say that a noun phrase can consist either of completely unordered words, or else it can consist of optional units A0 through A6, or optional units B0 through B6, where units A0 is just some sequence of words. I mean, basically, that's all we're just telling is that they're sequences of words. We're going to be training this thing off noun phrases that contain proper nouns. And so the goal here is just to try and see, can we learn some interesting internal structure inside of these noun phrases? This is sort of an example of some of the internal structure that this type of model winds up finding. You can see here, for example, that it's pulled out group A3 has turned out to be something like proper names, so the surnames. So you get Smith appearing inside of group A3. Because these groups can wind up being sequences of words, you'll see, in fact, it's actually sort of said, okay, one of these things like Van Dover, that's playing the role of surname. Group A2, again, I haven't sort of told it that group A2 should be something like middle initials, but it's decided that all the middle initials tend to play a similar sort of role. Group A0, you can see over here, are things like first names, but it's simply pulled out. A4, it's decided to actually use as suffixes like junior and stuff like that. Down here, you can see that it's actually learning structures of company names. So, the very last element of a company name is usually something like incorporated or limited or company. But you can see it's sort of starting to pull out prefixes and suffixes. And then it's also got this possibility of generating these sorts of names as just simply purely unordered things. So sports seems to appear all over inside of these sequences. So it winds up, in fact, actually saying that the best way to actually generate, these sort of sports names is not either parsing them as a company name or as a person name, but in fact actually sort of generating them as just sort of unordered sequences. Well, let's just see. I think I have to end by 5, right? So let me just say a little bit about inference for some of these things. Yeah. This was a very simple example. Right. If you had like deeper trees. So in fact, most of what I've worked on has actually been this word segmentation example here. So maybe I should just quickly go through that just to show you the type of things. Yeah, so let me sort of show you that maybe that rather than going through the inference procedure is the best way of spending the remaining time. So this is another sort of cog-sci type application, although actually people are using this for doing word segmentation in Asian languages now. So the idea is that a child learning language doesn't actually get to hear the spaces in between the words. So the input to the learner is going to be something that looks like this. You want to see the book. That's obtained by taking a transcript and looking each word up in a pronouncing dictionary and just basically concatenating all the words together. And then your task, the learner's task, is to figure out where to insert word boundaries, just simply using the purely distributional cues. So here you can see I've actually shown you what the correct segmentation would be. So how can we do this with something like an adapter grammar? So one sort of fairly straightforward way is to say, let's just generate a sentence as a sequence of words. Each word is a sequence of phonemes. And then now the adapter grammar is going to wind up learning essentially, if we wind up adapting the word subtrees, we'll essentially wind up learning the probability of each one of these subtrees. If you wind up just doing that, just simply adapting these word trees, and you actually ask what are the typical optimal segmentations, you get about 56% of the words correctly retrieved. So that's this unigram model. A slightly more complicated model would be to say, gee, let's actually imagine that we generate sentences as sequences of groups of words, and then each of these so-called collocations, and then each collocation is itself a sequence of one or more words. So this actually lets us capture some dependencies between adjacent words. So here, for example, in this little tree, you can see we're learning the book as a single unit, but we actually learn that it's a unit that's composed out of the unit for the word the, followed by the word book. Right? Does that make sense? So essentially it winds up doing type-based inference. So the type actually at this level is going to be the collocation level there. So you're not told what, I mean, it's one of the tricky things about these sorts of models is you're not actually told what the units are. You're going to learn those. And in fact, you can get even further. So here, you can see what I've done is I've said, okay, let's actually imagine that we have a collocation that's generated as a sequence of words. Each word itself is a sequence of syllables. Each syllable consists of an onset, a nucleus, and a coda. So basically what this actually says is in order to generate a collocation, generate a sequence of words. And I'm going to memorize this collocation. So the second time I see a drink, I'm not going to reparse it. Instead, I'm going to reuse that same parse. How did I generate the collocation a drink? Well, I generated it by generating a word. In fact, two words, a followed by drink. So how did I generate a drink? I generated that as an onset and a nucleus and a coda. So I actually learnt that by actually sort of modeling the syllable structure down here. It's not too surprising, right? I mean, in general, word boundaries occur at syllable boundaries. And so I'm actually learning what the possible onsets of syllables are, even though nobody actually tells me where the syllable boundaries are in the language. And that, as you can see now, all of a sudden our score's gone from around 56% to about 87% accuracy. So accuracy really sort of improves quite a bit. Yeah, so if we go back, let's go back to maybe like the simplest grammar here. So this is the one that just simply says that our sentence consists of a sequence of words. So after learning, the statistics that I wind up having to keep are the number of times that I've used each rule. So I've used, I've generated 15,000 words, but then I also wind up keeping statistics on the number of times that I've seen you as a word, 402 times, in 137 times, the doggy 100 times, that sort of stuff there. And so in a sense what I'm doing is I'm actually keeping track of the number of times that I've actually expanded word to that particular sequence. The top three rules are the input ones. So you as the grammar writer needs to write those rules, and you also need to say, and word is a good thing for you to memorize. And then the sampling procedure essentially does that memorization. So I think I had maybe not. But there was a slide here that said something about Bayesian hierarchy. It's interesting that the Bayesian hierarchy goes in the opposite direction to the grammatical hierarchy. So those of you that know something about hierarchical Dirichlet processes, essentially what happens is that the lowest level of the Bayesian hierarchy is at the very top level of the tree. If you need to generate a fresh one of these colloc 2s, you actually generate it by using the colloc as its base distribution. If you need to generate a fresh colloc, you generate it by using words as the base distribution, and so on like that. So in fact, it's interesting that the grammatical tree and the Bayesian tree actually go in opposite directions. Yeah, so that's the learning structure and names. Gee, I don't want to take too much more of your time up. most of the work that's required is actually sort of finding ways of making inference in these types of models more efficient. The data sets that are involved are still really rather small. You know, I mean, 1 million words is a big data set for doing Monte Carlo sampling on for this type of stuff. But let me just sort of give you a very high-level overview of this. Sampling procedures actually produce a sequence of samples from the posterior, and it's fairly standard in most work, just to simply, you know, run for, say, like 1 million samples, and then stop and take whatever the final, you know, in this case here is what the final parse trees are, and say that's my output. The right thing to actually do in Bayesian inference is instead actually to sort of run your samplers for a while and average over that output, right? That's, you know, if you read the textbooks, that's what they say you ought to do. If you wind up doing a very simple form of averaging over here, that actually gains you about 5 percentage points in accuracy. So that's actually sort of quite pleasing to see. These things are really sort of, it's a very hard search problem, search infrastructure. You know, I don't want to pretend that these things solve that problem. And in fact, exactly how you initialize the search procedure really matters. And one of the points is that with a sampling approach, there's a fairly tempting initialization, which is where essentially you generate the analysis of the first sentence at random. You generate the analysis of the second sentence conditioned on the one that you pick for the first sentence. You generate the third sentence conditioned on the analysis picked for the first two and stuff like that. That's what I call incremental initialization. That seems to be a very good greedy initialization. In other words, as against, say, just randomly initializing. The probability that you get by doing this incremental initialization is much higher. But at least in all the cases I looked at, I wound up getting stuck in some sort of local max. And that, in fact, I get much better results in the long term if I do a random initialization. And then this is really sort of, this table label resampling really actually has to do with inference procedures for hierarchical Dirichlet processes, hierarchical Chinese restaurant processes. When you have a very, you know, a fairly complex hierarchy, in order to get more mobility, it turns out that as well as actually sort of sampling parsers for individual sentences, it's also sort of fairly important to actually sample parsers for, sample the labels that are actually on the tables. That also winds up producing much better results. So, just to sort of wrap up here. So these adapter grammars, you know, they're called adapter grammars because they actually sort of adapt to the strings that they generate. And one way in which they adapt is because they learn the probabilities of whole subtrees, not just rules. They're non-parametric because which subtrees they learn depend on the data. The MCMC sampling procedures that are required here, you know, if you get the details right, you can wind up improving performance sort of quite significantly. And so we wind up actually, again, the competitors for this word segmentation task that I was looking at are generally around, you know, 60 or 70% accuracy. And we're getting around 87%. So thanks very much, guys. Yeah. So there's a guy up at Harvard, Tim O'Donnell, that's you know, that's actually sort of trying to do far more syntactic inference. The way that in order to make these the inference for these adapter grammars relatively efficient, I'm caching entire subtrees. So these are subtrees that go right down to terminals. So that's fine for these sorts of applications I'm looking at, where the things that you want to learn are things like words or morphemes or something else like that. Tim's idea is to say, gee, maybe these fragments that you want to try and learn can be kind of like, they don't need to be cashed out as terminals. That actually makes inference far harder. It's very easy for me to tell whether a fragment could potentially be reused in a string. I just need to see whether or not the terminal yield for the subtree actually appears in that string. And if it doesn't, I don't even consider that rule. Because, of course, this thing is essentially learning rules. I start off with a grammar that might only have 4 or 5 rules in it, but I wind up with a grammar that's got 50, 60,000 rules in it. But most of the rules are not, in the adapter grammar stuff that I'm doing, aren't applicable in a given string. What Tim's trying to do is, as I said, is trying to do this syntactic stuff, but he's facing this problem that he's trying to do inference with, this very, very large number of rules. And of course, he's finding that parsing is running extremely slowly. So yes, somebody is trying to, we are trying to do this stuff, but it's, I think it's hard work. There's a part of what makes this possible, I think, is precisely because the tree fragments which are being memorized. So actually what Tim O'Donnell is trying to do can be viewed as a statistically sound implementation of Renspod's DOP. Right? All right. Yeah. Yeah, yeah. So that's actually what I've recommended to Tim that he do, is that basically he because the unconditional inference, as I said, really seems to be too hard. So I've said, let's just imagine that you're just restricting attention to the trees that are given in, say, something like the Penn tree bank. And your goal is just to figure out what the fragments ought to be. So that should make inference much easier. If you actually condition on the trees, then if you condition, then all you really need to learn is where do the breaks appear inside of the trees. So yes, you can do that, and that should make inference, of course, much easier, and because it's supervised much better as well. Right, right, right. So before the high level, sure. I mean, there's nothing stopping you from restricting the search procedure, according to all those things. Yeah, yeah. So the high level story I sort of take on this stuff is that it's not as if we're the first ones to try and learn structure, to try and learn rules, right? But the previous methods are what I sometimes call the Chinese Revolution approach, the Cultural Revolution approach. So you let 1,000 flowers bloom, and you pick the possible rules according to some heuristic procedure that's not really related to the objective that you're trying to optimize. You let EM, this is what Glenn Carroll tried. You let EM then run for some number of iterations, and then you prune away the rules whose probability is below some threshold, and then you run your heuristic procedure again to try and see if it can propose some more rules to fix up errors. So in that sort of model, the rule proposal step really isn't integrated in with the actual model itself. The rule proposal step is just some additional heuristic procedure. And so I think the strength of this Chinese restaurant process stuff is it gives us a systematic way, essentially, of putting rule proposal inside of the learning algorithm as well. Right. So I think philosophically, it's trying to do something very similar to what Glenn Carroll and Andreas Stolke and all those people tried, all that time ago. But I think that it's for the first time, we actually now have a statistically sound framework for actually doing the rule proposal as well as the parameter search. That makes sense? So Stolke did the Bayesian inference, but just parametric. So here the prior is actually being used to propose the rules, right? So from 50,000 feet, the objective is the same. So yes, it's trying to do something that people have tried to do before. I'm sorry for putting you guys through this. I should have given the parsing talk. I should have just overridden you. I should have just said conditional random fields. Yeah. So right now I wind up using a Monte Carlo system where, essentially what happens is you need to run through the entire training corpus many times over, and essentially you wind up reparsing each sentence conditioned on the trees that you're currently guessing for each other sentence. Not in the adaptor grammar world, but just in terms of the non-parametric Bayes world, there's been a lot of work on variational inference, variational approximations for non-parametric Bayes. So in principle, I think those techniques ought to be applicable here. And then you get a much more EM-like update. In other words, what happens is that you need to parse you've got a set of parameters, you need to parse all the sentences with respect to those parameters. And since that's the most time-consuming step, that would then parallelize very well. There are interesting issues here because, in fact, actually one of the ways in which, one of the things that you actually often have to do in order to make these variational approximations is to, in fact, actually sort of truncate the set of, say, potential structures that you want to cache to some finite set of structures. And in general, I can't do that ahead of time. So one of the technical challenges that still needs to be faced here is that at each step you need to identify this set of potentially useful structures. Right. This would then actually make it much more like actually the sort of stuff that Andreas Stolke and Glenn Carroll were doing 10 years ago. There's some interesting work that's actually going on with Welling and UIT. So in terms of inference for these non-parametric Bayesian models, there are sort of two basic methods, sampling methods and variational approximations. And so basically what seems to happen is that the variational approximations are only accurate on structures which are seen, say, 5 times or more. Whereas the sampling methods actually become very inefficient as the counts get high. So basically sampling's a pretty good way of exploring, structures that you haven't seen before or structures that you've maybe seen once before. One of the problems with these rich get richer type models is that when the counts get fairly high, it can take a lot of samples to resample a table where there's 1,000 customers on. It takes at least 1,000 samples to move all the customers off that table. And in fact, because of the rich get richer attraction, you're actually fairly unlikely to do that. So variational approximations are much better on the high count things. And so Welling and Tay have started to develop methods where you use a variational approximation for the high count structures. So that's much more like traditional EM. But you use sampling for the novel structures that you haven't seen before. And that's, I think, sort of very promising because in applications like this, there's an infinite number of potential structures which I haven't seen before, but which might be useful, and so sampling seems like a very natural thing to do there. but variational Bayes should give you more efficiency as the counts get high.